In the last two lectures, we've seen an example of supervised neural nets, the multi-layer perceptron, and one example of unsupervised neural nets, Karhunen's self-organizing feature map. In the next talk, Dr. El-Sharkawi will present ancillary techniques for neural networks which improve the performance of any neural net type.
This presentation will deal with neural network and its ancillary technique as applied for power system problems. My name is Mohammed El-Sharkawi from the University of Washington, and this is my address in case you would like to get hold of me and you would like to discuss any of the topics of this presentation. And this is my email address also if you wish to contact me through the email. Now, the topic of this presentation is basically a collection of techniques that we should use as a developer of neural networks solutions to power system problems. The black box approach, which most people have used in the early stages of neural network, have proven to be the wrong way to approach the problem. And we have to address the challenges associated with the design, the training, and the implementation of neural networks. And I have here a list of challenges. I'm going to go through one at a time, and we're going to propose a solution to most of these problems. So what are the fundamental challenges? The first challenge would be the neural network structure. And with that, we mean the size of the neural network. If you look at maybe the multi-layer perceptron, then would be maybe the size of the hidden neurons. Because usually the input neuron and output neuron are decided by the problem you are solving. So for example, if you are doing a security assessment, the input would be the features that you will be using to assess the security of the system. And the output will be a security index. So the input and the output are usually determined. And then the hidden neuron is the only part of the neural network that you need to design. So how can we select that? In the early stages, you have seen people coming up with neural network structure that has hundreds of neurons in the hidden layer. And as we were going to see later on, that the complexity of the problem you are solving, especially in power system, may not require that large number of neurons. And basically, the large number of neurons may provide inaccurate performance for the neural network. The second part would be the learning protocol. And we have seen a number of learning protocol available down there. And I think my colleague who talked earlier about the neural network and the structure of the neural network, they talk also about the back error propagation, and we touched on other techniques. So we have to think about a learning protocol that would be suitable for the application we have. We're going to see later on, for example, that a back error propagation technique may not be the best technique if the problem you have an adaptive in nature and you would like to develop an adaptive training, an adaptive neural network. The third point would be the range of training data. And with that, if you look at the training data that you are using for the neural network, you have to be concerned about the range of the data and the distribution of the data in the operational space. If you have a wide data range, and then you have, for example, most of your data concentrated in a certain region in that span, and then in the other areas you will have a sparse data, then you are likely to have problems when you train the neural network and test it in the area where the data are sparse. So the range of the data and the distribution of the data are two important issues that should be considered before you design the neural network. The fourth item is the statistical property of the data. With that, I mean how much correlation you are going to allow between the input and output of the neural network. The output of the neural network should be highly correlated with the input. And if your input is not really correlated with the output, then the neural network will try to find a correlation. And this correlation, of course, will be wrong because there is no correlation to start with. Let me give you an example. If we assume that we are studying security assessment, and we know that maybe the voltage and current maybe in certain area will have an impact on the decision of the system security, then including those would be a positive step. However, if you include, for example, a load in a remote site that may or may not have any effect on the security, and having that an input, and you try to force a correlation between that particular input and the security status of the system, then you are likely to get erroneous neural network. The next challenge would be the formulation of the features. Most of the work done in neural network, the input to the neural network are either selected by maybe rule of thumb, or probably some engineers put their experience into it, and it can work this way, and it can be successful. However, in some cases, we are not really so sure about what feature we should use for a particular study. And let me give you an example again, maybe the security assessment. In the security assessment, we still are not, especially the dynamic security assessment, we still are not so sure what feature we should use in order to assess the dynamic security of the system. So this is still a challenge. It's a problem associated with the problem we are solving. Another example, in electric load forecasting, we know that the forecasting of electric load is dependent on maybe weather condition and the time of the day. So those are considered good features. But there might be other features that we are not aware of. And those features might have a better impact on the status, on the electric load forecasting. And so we have to use other technique that will try to extract those features and provide us with the best correlations between the input and output of the neural network. The next challenge would be the memorization of the neural network. With memorization, the neural net, I think Professor Marks in his talk touched on that. The memorization of the neural network is a situation where the design of the neural network is not adequate and the training of the neural network is not adequate. And you may even, with that inadequate design and inadequate training, you might be able to get a very small error when you train the neural network. But when you test the neural network, the error tends to be very large. If you have a situation like this, you might want to check if your neural network is memorizing the data rather than learning the data. I'm going to touch on that a little bit later on. Saturation, network saturation. This is also need to be closely observed in the network. You have seen before in the previous presentation that we have what we call it activation function, which in most part is a sigmoidal function. Now, this sigmoidal function is nonlinear and it has saturation in the upper and lower limit. If you allow the neurons in the network to saturate, mean to reach the upper and lower limit and stay there, then the network tends to be paralyzed and probably are not going to be able to train the neural network well in a situation like this. And I'm going to show you an example of that, and I'm going to show you how can we prevent this from happening. Sensitivity to variations in topology, operation, and control characteristic. Now, this is problem related to applications. I'm going to give you, for example, an example of a security assessment. With security assessment, we tend maybe to assess the security in the system, but if the topology and operating condition of the system changes, the security status might change with it. So in a situation like this, you would like to have a neural network that's insensitive to these variables, and that's a challenge. You would like to have your neural network to be adaptive to system dynamics. If your system itself is changing, you would like the neural network to follow that change. Give you an example. If you are doing load forecasting, and you are assuming that you are doing the load forecasting for the whole year, so you are doing load forecasting in the winter, and you are doing in spring, summer, and fall. Now, to have a neural network to do the load forecasting for all these seasons, 4 seasons, might be too much to ask. And most people probably will divide the season into 4 distinct networks. One for the summer, one for the fall, and one for the winter, and so on. The summer neural network probably will work well in the summer. The fall neural network will probably going to work well in the fall. But how about the transition between the summer and fall? This is not sudden transition. It's smooth transition. And in this situation, what is the neural network going to do? Which one you have to use? So probably you are better off if you design a neural network that follows a season. So the neural network itself would be probably designed for the winter, but when we go to the spring, the neural network will move to the spring configurations, and then when you go to the summer, it changed to the summer, and so on. So you would have an adaptive neural network in this case. Border tracking is another challenge. In lots of applications where we need to classify an output or classify problems into 2 classes, A and B. Example would be security assessment, where you have class A and class B. Class A probably secure, then class B will be insecure. So you have data from the secure class and data from the insecure class, and then you can very easily identify the security status of an operating point that would be in either of these 2 clusters. But if it's in between, you probably cannot do that. So in a situation like this, you would like to know what is the border of the class, and you would like to identify the class border. And that's, again, another challenge. So I'm going to go through some of these challenges and show you the problem, and then show you some of the solution that you might want to implement to prevent that from happening. Learning versus memorization. Let's look at this graph here. Let's assume that we have a very simple case, y versus x. And assume that we have a data here. And the data will be those dark points that you see here. These represent the data. And you would like to do some kind of interpolation of this data. So one good interpolation would be is this function f1. It's a very smooth function, and it passes through the data. You have it here, and the error is reasonable error. And I think probably I can get this function if I use Taylor expansion, and I can use probably 3, 4, maybe maximum 5 terms of Taylor expansion, and identify the parameter of those based on the data. I probably can get f1 very easily. However, if I increase the number of elements in the Taylor expansion, say to 10, 15, or 20, so now we are having a very complex model and highly nonlinear model, and I would like that model to fit the data. You have it here, and I identify the parameters, and I use, of course, cost index to identify the parameters. But I kept the identification process going to minimize the errors in the parameter identification. And if I do that, I'm probably going to get with a function like f2, which will pass through every single points that was collected in the test. Now, this function here will give you probably a 0 error in training. But let's assume that f1 is the truth. That's a true separation between 2 classes. The class above it, say class 1A, the class below it, say class B. So if I test a network, or I test a function like f2, and I have a point here, now this point would be classified as B, while in the true case is classified as A. So in a situation like this, you are going to have very large testing error and very low training error. And there will be two mistakes we have done. The first mistake is that the Taylor expansion is much more complex than it should be. The second mistake is that we trained or we identified the parameter, or the identification process of the parameters was going on for longer than it should be. So these are two critical mistakes. Now let us map that back to the neural network. If we have a neural network, and again, like what I said before, the hidden neurons are basically the one that we can design. So if you have large number of hidden neurons, that means that you have a complex function with large number of elements. So this would be equivalent to function F2 in the two-dimension case. So having large number of hidden neurons may not be a good way to design a neural network. So actually you are better off to have a smaller number of hidden neurons in a situation like this. And also if you have large number of hidden neurons and you kept training the neural network to reach the global minima, that may not be the right way to do it. So these are the two mistakes that could happen in neural network training. The size could be larger than it should be, and the training takes longer time than it should be. How can we prevent that from happening? Well, there is a very easy way to do that. What I would do in a situation like this is that I get my training data, and I probably going to shuffle them and divide them into two subsets. One subset would be 90% of the data, and maybe the other subset would be about, say, 10% of the data. And I'm going to call the first subset training data, the second subset verification or testing data. So what I do is that I iterate, maybe every iteration or every few iteration, and then let me go to that figure and explain what we could do. If the y-axis represent the error of the neural network, and the x-axis represent the iteration, and this red curve here represent the training error, and this blue curve represent the testing error. Remember, we are testing on only 10% of the data. So for example, after a few iterations, you're going to see that the training error is going down. The testing error also is going down. Then what you do, you stop, you shuffle the data, you randomly divide them again to another 90% set and 10% set, and then do that training, maybe a few more training iteration this way. So you go here, and then you're going to see also the training set is going down, and the testing set is going down. And you keep doing that. You're going to find probably the training set is continuously, or the error of the training set is continuously going down, and the error of the testing set will go down initially. It might bounce back a little bit, and it goes down again, and then start diverging. When it starts diverging here, this is your best point to stop. At this point, you have the minimum testing error, and you have a good training error. And you stop here, and that would be a good, a well-trained neural network. Now, you take that neural network, and I assume that you are going to have another file that contains test data, and then you can use that file to test your neural network. And if you are happy with that, then you are successful in your mission. Neural network size. Well, as I mentioned before, you probably don't have a control on the input and output dimension of the neural network, the input neuron and output neuron, that's it. So the input neuron is determined by the application you have, and the output neuron also determined by the application. The only design that you really have in the neural network, I'm talking about the multi-layer perceptron, is the size of the hidden layer. How many neurons would you allow in the hidden layer? Now, the rule of thumb is that the number of hidden neurons must be matched to the complexity of the classification boundary. This is very important to keep in mind. So if you are looking at a situation like load forecasting, for example, And in load forecasting, you are looking at the function that you are going to get as an output for load forecasting. You're going to find is fairly smooth function. Is that you probably have two peaks, one morning peak, one afternoon peaks, and you have probably in the middle of the day where you have the minimum load. It depends, of course, on the area that you are talking about, whether it's industrial or residential. But in most cases, it's very smooth function, and probably doesn't require a large number of hidden neurons. So the complexity of the problem is very important to be matched to the size of the neural network that you have and the number of the hidden neurons. That's very good, but how can we achieve that? Well, the easy way to do it is by cross-validation. And by cross-validation is that you test different types of neural networks and find out which one will give you the best result. And I'm going to show that in a second. So what I would like it to do if you are going to start designing a neural network, I would like to do something like this here. If in this curve here, I have a y-axis and x-axis. The y-axis represents the error of the neural network after it's fully trained. And then the x-axis would be the number of hidden neurons. Now, try with very small number of hidden neurons and see and figure out the error. You're probably going to find large error. Then increase the number of hidden neurons. You're going to find it's going down. And then it will be flat for a while, and then start going up again. Why that's happening? Well, if you have a small number of hidden neurons, then your model is not adequate. I'll give you an example for that. If the system is nonlinear, and you are using Taylor expansion, and you're having only 2 terms in Taylor expansion, that's linear. So the linear model is not going to really represent the nonlinear system. And the degree of nonlinearity can vary from case to case. So that's a simple example. So here, what this curve is telling us is that the model that we are using, or the neural network structure we are using, is probably not adequate, and we need to increase the number of hidden neurons. Here it tells us that basically any number of hidden neurons in this range will be adequate. Now here, look at here. Now when we increase the number of hidden neurons, the error tends to go up, and the reason for that is memorization. We are having large number of hidden neurons than it should be, and this is a form of memorization. We should avoid that. So this is probably a step that you have to do before you start becoming serious about the application to the particular problem you have. Network saturation. Now, if you look at the activation function, it looks sigmoid this way. It can be actually bipolar, or it can be monopolar. In this case, you have the function, sigmoid function, in the y-axis versus the input in the x-axis. And as you know, you collect all the input from the upper layer, and then you add them up in a weighted fashion, and then you can process it through a nonlinear function like this, or some people call it squashing function. Now, if you look here, you see that there is a saturation range here. There is a saturation range here. Now, in this saturation range, if you look here what's happening, a wide variation of an input here probably is not going to change the output by much. And here also the same thing. A wide variation of input is not going to change the output by much. So the network in these two cases here, either upper saturation or lower saturation, they are not going to really produce any output result for a wide range of inputs. So the network is not sensitive, or this particular node is not sensitive to the input. Your best bet if you are in this region here, where a variation of an input can have an impact on an output. Now, is it bad to have the nodes in the saturated region? Not really, unless you have larger than it should be, larger number of neurons than it should be are in the saturation region. So what is the rule of thumb? I don't know. It's say about 25% of the neurons. You allow up to 25% of the neuron to saturate, and then it should be okay. So let's recap. The saturation when you have the nonlinear function reach its limit, either upper or lower limit. And in this case, a wide change in the input produce minimal or no change in the output. If you have large number of saturated neural network, the neural network can be paralyzed. Paralyzed means that the output of the neural network may not be sensitive to the input in this particular range. Now, what will happen if it's saturated? Very simple. You should randomly disturb the weights for that particular neuron, and then you continue with the testing. But it should be monitored, and should be monitored very closely, and you should not allow more than maybe, say, 20% of the neuron to saturate. If they saturate, perturb the neuron that are saturated, perturb the weights that's connected to the neuron that are saturated, and then continue with the training process. The next topic is feature extraction. Most of the time, engineers probably will be able to give you very good features for the application you have in mind. We did some work for Puget Power in Seattle area, and the work was in load forecasting. And when we started doing the work for them, initially we decided to come up with feature ourselves. They told us that they have a person at Puget Power that literally check the weather condition, and then he can come up with electric load forecast. He has a feel for it more than anything else. And he has a very good result. And we decided to start from scratch, and we decided maybe we should come up with our own features, and we did that. And when we test the network and compare it with that person over there, we did very poorly. And then we went back again, and we tried to change our inputs to the network, and we didn't have success. And then in the end, we went to that person and asked him about the feature he used. And when he gave us his features, and which was really interesting features, and they were not direct temperature, it was deviation of temperature than direct temperature, it was thermal inertia, things in that nature. And when we use that in the neural network, we managed to get very good results. And in all these cases, the network was almost the same, has the same number of input, same number of output, same number of hidden neurons. It is just the input was different in these cases. So extracting feature is very important, and I have seen probably a lot of people that make a strong conclusion on the neural network based on their features, and basically they attribute the success or failure of the neural network to the neural network itself, not to the features. So I think we should first look at the feature we have. They have to be highly correlated with the output, and if they are not, then the neural network will not going to give you a good result. So, so what you would like to do, you would like to train a neural network with reasonable accuracy. If you want to do that, then it is obvious that you have a sufficiently large data set that must span the operating space be available. You should have that. And those data should be highly correlated with the output. Now, if you don't have that, if you don't have correlated data, then you should think about using feature extraction to try to come up with correlated data for you. So you have two options here. Either use experience, and I'm talking about verified experience, and or using mathematical feature extraction. So, and I'm going to talk a little bit about mathematical feature extraction in a second. So let's recap. Why do you need feature extraction? First, feature extraction will tend to reduce the number of your inputs. So this way, if you have a curse of dimensionality problem, then you are eliminating that. And feature extraction will enhance class separation, especially if you are doing classification problem, and reduce the pattern dimension and maintain classification accuracy. Those are the main reasons why you should use feature extraction. How can you implement that in a neural network? Well, here is an idea. You can start basically with input data, and that could be any data you have. And of course, you know that data has to be normalized. And then after it's normalized, you go to the feature selection. where you actually extract the feature either mathematically or by using other techniques. I'm going to show, or using some kind of an expert system or experience from an operator. But once you achieve that, you would like to train the neural network with the feature, not with the data, but with the features. And then if the result is acceptable, you are successful. If not acceptable, you go back again and modify your feature, either increase it or reduce it until you get the right features for your application. I'm going to talk about two methods for feature extraction. The first one, we'll call it class mean feature extraction. And in this case, we are assuming that you have two classes. The first class would be maybe, let's talk about security assessment again. So the class 1 might be secure, class 2 might be insecure. So you have two classes. Now, what you would like to do, you would like to include variables as an input that will make a difference. For example, if I have a power system and I have a transmission line here, and I have a fault on the transmission line, probably, the flow in that line before fault is very important in determining the security status. If the line is lightly loaded, then the system might be secure. If the line is heavily loaded, then the system might be insecure. If that's the case, then that current or that load or that flow in that line is very important in determining the security status of the power system, and that should be included. And in this case, that particular feature, which is the line flow, will create a big separation between the two classes, between the class 1 and class 2. If you take another variable, for example, a load in a very remote area and it's very small load, and if you find that if that load is 100% or 0%, is not going to make any difference in the security status. So that particular variable is not going to separate the two classes, and you should not have it in your data to start with. And including that in your data actually will have a negative impact on the training of the neural network. So what we're looking for here, we're looking for variables that can create a big separation between the two classes. So before we go to the math, let's summarize what we talked about in class mean feature extraction. It is actually a heuristic measure of interclass distance. So you look at the distance between two classes, class 1 and class 2, and the dominant indices are selected. If it's done properly, then the result is that you are going to include the dominant indices or dominant variables. And the dimension of the pattern vector can be reduced. And the last item is that the pattern vector for each class occupies a distinct region in the observation space. And that would be a key point before you start the training of the neural network. Well, how we do that mathematically is very simple. All you have to do is to calculate the distance. So if you assume that this is your original pattern, big Y here, that has a vector of a small y's, assume that the first Y here is maybe voltage at some bus. This Y here is probably current in some lines, and so on and so forth. So we don't know if that voltage or that current or any other variable or any other variable will have an impact on the security status of the system. So you start with something like this, and then you calculate the interclass distance, which is basically would be a simple distance function that has a separation between the two classes, class 1 and class 2, and this is the mean or the average value that you can get, and this is the deviation, standard deviation of that, and you square that, and this will give you the distance. And again, the M is basically a simple average of that particular value. If you're talking about that voltage, so the average of that voltage for all the data, you have to go vertically. And this is a deviation equation, and that's the way you do it. So you look at F, and then you pick the variables that provide you with large value of F. And F actually should be larger than the distance between the two centroid of the two variables. And the centroid in this case is classified by M. Well, it looks like a very simple process and can be quickly done. And the advantage, let's go through the advantage and drawbacks of this technique. If you look at the advantage, you're going to find that the class mean feature extraction is very simple first order statistics. And also you're going to find another feature is after you reduce or you eliminate the unnecessary variable, the rest of the variable still have a physical meaning. The rest of the variable will still be the currents, the voltage, or whatever. So they still have a physical meaning, and engineers always like to have variables that have physical meaning. Now, what is the drawback? The drawback is that the data must have an interclass distance. I'm going to give you an example where this technique might fail. And actually, in case of concentric data, this technique would fail. And this is an example where you might have a problem with this technique. In this case here, we have data that occupy distinct region. Like this data here, in the blue region here, occupy probably class 1. In the red here, occupy class 2. And if you look at the class 2 is distinctly in this area, class 1 is also in this area. There is no actually mix between the two classes. But if you calculate the centroid of the red and the blue, they're going to be probably the same. So even so, they occupy two different distinct regions. They don't have interclass distance. So the basic assumption here is that you have to have an interclass distance to be able to use that technique. Most of the security assessment cases that I have tried myself, they don't have this problem. They don't have this problem. Actually, it was very clearly a distinct region in the operating space. Another technique that you might want to think about is Karhunen-Loe expansion. That's, again, a second technique for feature extraction. And power engineers probably will be able to recognize this technique very quickly. This is what we call it modal approach. And this is a technique that we have used in power system probably in the late 60s, and it was very popular then. It's exactly the same technique. I'm going to walk through the steps with you here. So if you assume now that you have an original pattern here that looks like this, X is an original pattern, and we don't know if it includes data here that's highly correlated with the output. So what we can do, we would like to be able to reduce that pattern into a smaller pattern called Y. The dimension of X is N, and the dimension of Y is D, and we're assuming that D will be smaller than N. So in this case, you are reducing the pattern, and also you are trying to eliminate data that's not highly correlated with the output. So what you do, how you do that, it's very simple. You look at the original pattern here, that's the X we have, and then we do the pattern mapping, which is basically try to come up with another X, hopefully is the same like this X, and it's equal to this function here, which is a Y multiplied by phi. Phi is a matrix, and it's called orthonormal function. And the condition for that matrix is that if you multiply the transpose by the matrix itself, should give you 1 for the same matrix and should give you 0 if the matrix is for different data. So, and that's basically the concept of modal approach, is to try to find this phi so that I can invert it and put it here and come up with the Y that represent X. So hopefully the sigma of Y times this matrix phi here will give me the X, which is equivalent to the original pattern. Now, how do we do that? Well, it's like any optimization function. You try with an error index like this, and the error index would be the expectation of the original pattern, X, minus the approximate pattern. And of course, transport, you have to do it twice, multiplied to get the square out of it. So it's form of least square technique here, but you do it on the expected value. And what you do is that you minimize J in this case, and you try to find phi that will minimize J. And if you select the right phi here, then this value here tends to be very small, and then J would be minimum. Now, if you do the math, you're going to find that, yes, you can find phi that will minimize this function. And phi would be basically the eigenvector of the expected value of the input vector multiplied by the input vector transposed. And in this case, the minimum value for that function would be the eigenvalue of this. So what you have to do is that you start with this function, and then phi in this case would be basically the eigenvector of your input vector. And once you achieve that, you already achieve your reduction. So let's summarize the Karhunen-Loe expansion. The reduction is second-order statistic. We are using the eigenvalue and eigenvectors here, using the variance. And the linearly combination of original set are done to form a set with better separation and with better features. So what you are doing is that you are getting the original feature, and basically you mix them together and come up with another set of features that have a little bit of everything, but are highly correlated with the output. Now, what is the problem with that? The problem that I can see with that is that the new features that you are going to get after you implement the Karhunen-Loe expansion, the new feature will not going to have, are not going to have really a physical meaning, because you did the process through eigenvalues, and the weighting of the eigenvalues and eigenvectors will be mixed in that process, and you probably are not going to be able to have any physical meaning for this feature. If that's not a problem, then Karhunen-Loe will be a good technique for feature extraction. I would like to move on to a next topic, which basically inversion of the neural network. How do we invert the neural network? But before we do that, what I would like to do is I would like to mention, why do we need to do that? Well, you probably need to use the inversion technique for two reasons. Well, before we get into that, the inversion technique is basically flip the neural network. So the input becomes output and the output becomes input. So in this case, you give the neural network the output you want, and the neural network will tell you what input should be there. And why you do that? Well, you do that for two reasons. One reason is that if you assume that you have multi-class system and you want to create the boundary, let's go again to a simple case where you have two classes, class 1 and class 2, or secure or insecure. Let's assume when you train the neural network, you give 1 to secure, you give 0 to insecure. So assume that 0.5 was a border point that can go either way. Now, your data that you have is secure and insecure, and it will cover two clusters. But you probably don't know the border points, which is 0.5. Then here it comes the inversion technique. You might, if it's done correctly, you might be able to give the neural network as an input 0.5. So now you are flipping the neural network. The output becomes input and input becomes output. So you are telling the neural network now 0.5. Tell me what is the operating point that corresponding to 0.5. Of course, the neural network give you number of these operating points, and then you can test them and see if they are actually border points or not. If they are border points, then you can include them. If not, then you can exclude them. So that's one reason why you should use inversion of neural network. Another reason which is probably more common is most of the time we don't have sufficient data to train a neural network. You might have a data in a certain space in the operation, in certain areas in the operating space, but you probably don't have enough data to cover the entire operating space. So in this case, what you would like to do, you would like to ask the neural network to tell you which area that the neural network need more data on. So you start with a small number of data and let the neural network tell you the areas that need extra data. So when you generate the data files, then you concentrate on these areas. And if you do it this way, you will have a training data that's really manageable in size and uniformly distributed in the space, in the operating space. So the inversion of neural network, before we go to that, let's go to the basics, which is the accuracy of a classifier is dependent on the amount and quality of training data. That is very important to keep in mind. The amount, you have to have sufficient training data that span the operating space. You have to quality of training data. You have to have a training data that's highly correlated with the output. That the input of that training of this training data are highly correlated with the output. The training data should be sufficient to cover the entire space of the system operation. So keep that in mind. So let's see how can we do the inversion. Now let's assume that we have a situation like this. In this case, we go back to the security issue. Assume that your power system have two distinct regions. The first one is called secure region. The second one is called insecure region. And your data are in this region here, in the secure and insecure. So you have your data in this region here. So you know, when you test the network, if you have a data here, you can classify it secure. You have a data here, you can classify it insecure. But there is a gray area in between. This gray area could be narrow or could be wide. The gray area might be acceptable to the operator because he probably want to do a detailed analysis in the gray area, so he doesn't mind that. However, if the gray area is really wide, you would like to narrow the gray area a little bit. So in this gray area, we call it region of confusion here. So what you would like to do if the neural network is trained based on secure and insecure data, you would like to be able to invert the neural network so the network can actually draw a border line between the two regions. So how do we do that? Well, this is a simple algorithm that we might want to consider for this application. You start here with the input pattern. You train the neural network with whatever you have. You invert the neural network. And after you invert it, you check the data that the neural network gave you through the gradient, computation, and oracle. And I'm going to talk about that in a second. Well, the concept of inversion is not really new, or it's not really that difficult to understand. Let's look at this figure here. Let's see what we do generally with neural network. In general, what you have an input space and you have an output space. The input space is X, the output space is Y. Now with neural network, you go from, when you train the network, you go from X to Y by identifying the network weights. So what we know in this case, we know the X, we know the Y, and then we identify the weights. That's what we do with training. Now if you want to invert the neural network, you would know Y, okay? You would know the weights, and you identify the input. So you still know 2, and you identify the third one. Well, can you do that mathematically? Actually, you can. And it's very simple to the back error propagation technique. The same algorithm used for back error propagation can be used for inversion. And let me show you why. Usually, in the back error propagation, for example, we have the error function that basically looks like this, which is the difference between the desired value and the output value of the neural network. You square that because it's a least square method. And so this is the error function you have. When you update the weight, what you do, you look at the weight at step k plus 1, which is equal the weight at step k, and then minus a small number or a small value or a small step size multiplied by the derivative of the error function with respect to the weight. And that's how we identify the weight. Now, if you want to identify the input in the inversion process, the weight will be fixed. And then the input at step k plus 1 is equal to the input at step k, and then you have a step size multiplied by the derivative of the energy function with respect to the input, not with respect to the weight. And if you do the math, you find that this function here has a similar shape than this function here, and you can do it very well through the back error propagation algorithm itself. Well, then now we inverted the neural network. So you had an output, you gave it to the neural network, and the neural network gave you an input. Now, what you would like to do, you would like to verify the input or the operating point that the neural network has given you. And you would like to know if this is belong to secure or insecure or in the border. So assume now that this is a boundary between the two classes, secure and insecure, and assume that the neural network give you a point here. Now you want to verify if this point is in the border or not. So you go a certain distance here on each direction, and in one direction here you go a certain distance, you get a point called Q. You go and same distance in the other direction, you get a point called P. And then you check point Q and point P by querying your system. And if you find that these 2 points belong to the same class, then the point that the neural network has given you is really useless. But if you find that these 2 points belong to different class, then you might want to use that interval halving technique and zoom and figure out the actual point on the border. And once you know that, you tag that point, and then you move on to the next point. Now, the question is, how do you go into that distance? That distance is basically 1 over g. I'm going to show you what is g here. G is calculated by first calculating the gradient of y with respect to x, which is nothing but the derivative of y with every single x, or every single input like that. And then you calculate j, which is very close to the RMS value, root mean squared, that we get it for the derivatives that you have here. So when you do that, that's what will happen. Initially, you're going to start with a system like this, that you have points in one class and point in another class, but you don't really know the border that separate the two classes. So that's the starting point here. And when you do the inversion and you do the query, you will end up with a system that looks like this. And here what you have the same original points, the red and the blue here, and then the inversion technique and the query will come up with those yellow points here that identify the border. Once you did that, then the border is identified, and at least in theory, then it encompasses one class and separate the both classes together. Now I'd like to talk about 2 other techniques that you might want to consider for neural network development. The first technique is called genetic algorithm, and the second one would be fuzzy neural network. With genetic algorithm, the objective is to try to find alternative training techniques and or better initial conditions for the neural network training. The genetic algorithm, as it shows here, is needed because the standard single search technique like back error propagation may trap the neural network in undesirable minima. It could be a local minima, but undesirable local minima. And the convergency will depend on the initial conditions that you have used for training of neural network. This is true for back error propagation and similar training techniques. Well, but we all know that the back error propagation performs within network structure, and that's very good features that we would like to maintain. But also we know that the back error propagation have number of limitations. And among this limitation is that it's obvious that it's not adaptive technique, because what you are doing is that you are getting the training data all pass through the system at the same time, and you can repeat the same data and you iterate using the same data until you are converging. There is no really room for adaptation unless you modify that back error propagation technique itself. So all the data must be used for every update. Now, the problem with that is that if you have irrelevant data that's in your data set, you cannot really remove it directly with back error propagation. You have to go to the data itself and remove it yourself before you give it to the neural network. So the network cannot really forgive and forget those kind of data. Also, importance of data cannot be easily weighted, And give you example for that, when you do load forecasting, you probably you're probably very interested in the peaks rather than the values of the electric load forecasting curve. And the peaks will require probably emphasis on on this particular time where you get a high demand for the electric load. Fuse back error propagation, emphasizing that might be a little bit difficult, and you might need to do extra work in order to get the effect of weighted data. And if the size of the neural network is not adequately selected, it's going to take forever to train the neural network on a very simple problem. Well, let me show you this slide here, and that can compare two techniques. One of them would be the back error propagation techniques, for example, or single search technique, and the other one will be a genetic algorithm used for training of a neural network. Now, let's assume here that we have a problem, x and y problem, that you have two variables, x and y, and what you are seeing here, you're seeing the contours of the energy function that we are trying to minimize. And this is like a view from an aeroplane of that energy function. And as you see here, you probably have three minima here, one there, and one also here. Now, assume that when you start training, your initial condition was here, then you are very likely that you will converge to this minima. If your initial condition is here, you are very likely to converge to this minima. And if your initial condition is here, you're likely to converge this minima. So the convergency probably will depend on your initial condition. Now, genetic search is a little bit different. It starts with a set of data that are distributed. I don't know if you can clearly see the color here, but let's see, maybe this is red here. You have 1, 2, 3, 4 red marks here. Maybe you start with that, and then you evaluate those points. And then if they are not acceptable, you will generate another set of points in a systematic way. I'm going to show you that in a second. And these probably are the blues. And then you evaluate that. And if you don't like it, you generate another set of data, and so on, until you find a set of data that probably will get you to the global minima here, or very close to the global minima. And this would be basically a convergency, or at least a very close to convergency. Now, if you receive a data here, you're probably going to you want to either stop here and use the weights of the neural network that identified by genetic algorithm to be the weight of the neural network, or you can use that as an initial condition and use back error propagation to converge you further into the global minima. Now, to do that, you probably will start, this is basically the jargon of the genetic algorithm. I'm going to explain that in a second. But what you start with initial population, which is basically initial points. And then you do the fitness, and you select from that another set of data. You do the crossover and mutation. I'm going to explain that in a second. And then after you do that, you check through the network. If you're happy with the result, you stop. If you don't happy, you go back again and you iterate until you receive what you want. And of course, when you train the neural network, you are using the training data that you have, and you also have the testing data to test the neural network. So the key operations here would be the input pattern. You evaluate and you select variables. You do the crossover, you do the mutation, you come up with a new generation, and you keep looping here until you are happy with the result. Now, this is how you start, and I'm going to zoom into the population. But let me show you here what we are seeing here in this slide. You first start with population pool, and the population pool will have individuals. And the individuals, in this case, would be initial conditions. So it could be random initial conditions for the neural network. So population 1 will have a vector of all the weights of the neural network. And vector 2 will have another initial condition of all the weights of the neural network, and so on. So you have here, in this case, 1, 2, 3, k number of individuals. Now let's zoom into the individual and see what we have here. Now let's look at an individual here. Individual is divided into bytes, and each byte would be a weight. Like in this byte here would be the weight W11 maybe. The next byte would be the weight W12, and so on and so forth, until the last byte will be weight Wij, which is probably the last weight you have it in the neural network. Now, if you look inside the bytes, you have a binary number here, which is basically a sequence of 0 and 1s, and that can be translated into actually crisp number. So what you are using here, a binary number, represent the byte. So you end up with population pool or initial conditions, if you wish. Then the initial condition will include all the weights for the neural network and include several values for the weight of the neural network. So these are the individuals. And then we go to the parent selection. And if you look at the population pool, this is the original population pool that has individuals here. Then you have to have a way to basically judge the importance of these weights. There is a number of ways that you can do that. You can quickly check the initial weight, put them in the neural network, and check the result of the neural network and how far you are from the minima. And then you pick the one that can give you probably a good or a small error compared to the others. Or you can do them in roulette wheel technique like here, where you keep spinning, and the one that shows the most is the one that you select, again based on what is the neural network will give you based on only the initial conditions. So now once you did that, you come up with new population pool. Now the new population pool can have repeated individuals. So we call those new 1, new 2, new 3, and so on and so forth. So among these, you pick the one that's selected most by using maybe the roulette wheel technique, and assume that this is individual number 3, and this is individual number 8. Those are the two new individual, and we are going to call those two individual parents here, and we're going to pull them out as shown here, and those becomes the 2 that we're going to start working on. So these are the parents that we have two individuals here, number 3 and number 8. Then these two parents, we're going to do the crossover and come up with what we call it children. And this is another initial conditions that's based on the parents by doing the crossover. How do we do the crossover? It's basically, if you remember the string, the byte itself is a string of 0s and 1s. So you come at one point and you chop it, and you take the second half of one string, put it on the second half of the other string, and you swap. So you swap maybe the second half of the strings in both of those, and that would be the crossover. Also, you might want to do mutation, so just to get away from the sequence that you are having of the new generation or new children, if you will. And the mutation is done very simple by basically altering one of the genes that you have, or one of the binary numbers you have, from 0 to 1 or from 1 to 0, and then you come up with mutated children this way. So by doing that, and each time you come up with new individual, you test them, and you see how well they are doing in terms of accuracy as far as error is concerned of the neural network. And here I'm going to give you an example. For example, in this case, we have 4 generations, generation 1, 2, 3, and 4. And this is the error that the neural network will provide you. This is the minimum. I don't care about the maximum. So when I look at the gene number 1, generation number 1, I'm sorry, this would be the minimum that they give me. Generation number 2, this would be the minimum. Generation number 3, this is the minimum. And this is the minimum. So if you look at this here, it's very clear that I would pick generation number 4 to be the initial condition for the neural network. And if I do that, Let me show you a comparison here, a case studied. And in this case, I would like to zoom a little bit on the curve. And what we're having, the neural network error versus the iteration. And this is what will happen if you use back error propagation technique. And this is what will happen if you use genetic algorithm. Maybe you go maybe about, I would say, 2 or 3 generations. You don't really need to go more than that. And you come up with initial condition. If you use that initial condition, you can see that you can converge much faster and converge to a better minima. So this is a very promising technique, and I would encourage most of you to try it, at least to come up with the initial condition that you would use for back error propagation later on. The last subject that I want to cover is fuzzified neural network. The fuzzy technique is becoming very popular in a number of areas, including controls and including classifications and so on and so forth. But also neural network is becoming more and more popular in neural network applications, either by developing a structure of neural network based on the fuzzy logic itself, where you can get the fuzzy logic and then you implement it using neural network. Or you can use the fuzzy logic as a filtering technique, and that's what I'm going to do today, is that show you how can you use the fuzzy logic as a filter for the neural network. Now, when you use fuzzy logic in this case, is that when the information on whatever decision you want to make is incomplete or the reliability is uncertain. Fuzzy logic is mainly used with neural network to increase the dynamic range of the output neuron and reduce the effect of data noise. And I'm going to show you an example of that, is that in a case where we had might have some noise in the data, you're going to find that using the fuzzy logic might help in eliminating the effect of this noise. And also in a situation where you might have larger number of outputs, and if you try to do fuzzified neural network or fuzzy neurons in this case, you can see the size of the output can be reduced substantially. How you implement fuzzy logic in a neural network structure? Well, again, you have to use an algorithm that might look like this. You start with the measurements or the data, and you prepare the data, whatever method you're going to use for preparing the data. That might include feature extraction or fuzzified neurons. So you fuzzified the data, you train the neural network, and the output is also fuzzified. So if you want to get real output, defuzzify that, and you get the output. If you're happy with that, stop. If you're not happy, you can iterate until you get the result that's acceptable to you. Let me give you here an example on how to use fuzzified neural network. In this case, in this particular study, a neural network was designed to identify shorts in a turbo alternators that's used in power stations, in thermal power plant. And in that particular turbo alternator has about 238 turns. And the objective was to try to identify the turn that has the short. So if you look from the basics of the neural network, it would be maybe easy to assume that the neural network should be designed with 238 outputs. And each output will be identified with one turn. And if it's 0, then it's healthy. If it's 1, maybe it's short. So that your output now becomes 238 neurons. And probably if you try to train the neural network and come up with a result, you probably are not going to be happy with the result you are going to get. And probably the neural network is not going to work as adequately as you hoped it would be. But what you can do is that you can design the neural network to have only 5 outputs. And each output might be correspond to, say, 47 turns. So the first output will be corresponding to first 47 turns. The second output will be for the next, so on and so forth. Now, what you do is that you come up with a membership function. We said we have 5 output neurons. So this, the result of this guy here, would be the output of neuron number 1. and the result of this one here would be the output of neuron number 2, number 3, 4, and 5. So instead of giving a crisp output for each turn, what we do is we give fuzzified output. This is called membership function. So in a situation like this, like assume that we have a short in turn number 75, 75 would be here. So neuron number 1, you go from here to here, neuron number 1 will have this value here, which is 0.4 of the peak, assuming that the peak is 1. And then the second neuron will be here, and it's going to have an output of 0.6. So what you are having here, you are having two outputs. The first output of this neuron here would be 0.4. The second output would be for this purple neuron, it would be 0.6. And the output of the rest of the neuron would be 0.7. So what we are doing mapping, basically. Mapping from the linear scale into the fuzzy scale. So instead of having 238, now we're having 5. But the result we have it, if I get a result 0.4 for neuron 1, 0.6 for neuron 2, that translates into 0.75. And in this way, you have eliminated the size of the neural network, and you enhance the dynamic range of the neural network. So the output of the neural network, let's recap. The output of the neural network is divided into fuzzy groups. In this case was 5 fuzzy groups, and each output neuron correspond to a membership function, and training is done to recognize the membership value of the output neuron, not necessarily the crisp value of the original set. And the output of the neural network is defuzzified when you test it, and each membership function is weighted. And basically, the weighting you are doing with the first momentum technique, which is widely used in fuzzy logic. This is by no means was designed to give you all the information you need on this technology. But what I'm trying to do is I'm trying to give you some ideas on how to use other technologies and apply that to the neural network. And I would like to conclude my presentation by these points here. The first one is that the application and implementation of neural network are complex and sophisticated. It is not a very straightforward problem, and the open loop black box approach, which unfortunately a lot of people are doing it, is not really acceptable. Black box approach in the design, training, and verification can no longer be acceptable. And any neural network can be enhanced when some ancillary technique has been used. Thank you very much.